And I'm very excited to be here to share some of my latest thoughts on the foundation models, especially like now we try to not only just do reasoning, but also do agentic tasks. So I want to talk about like if we try to make the large language model to be able to perform like agentic tasks, what kind of reasoning do we need to do? So for the agent task, the first thing we want to talk about is how we can define the agent. Essentially, the agent is trying to perform many tasks in many environments. So there are two aspects we want to capture. The first one is we want to do the goal-driven decision making so that the model can perform many tasks. And then we want the model to actually adapt to different environments. So this is mainly about interaction. And this actually will help the model to transition from this language model to the agent model. So we will center the entire talk based on the interaction with the environment and how the model can learn decision making. This is a very interesting example that I just tried to ask the model to set up the table, and they will predict like I want to put the turkey on top of the table, and then the model just directly puts the turkey on top of the table. So this is something like very surprising to me that as human we will never do this because we will ground the prediction into the environment and we will actually use the plates. So if we ask the model to use plates, they will do the replanning and they will mention, oh, we should put the turkey on top of the plate and then put the plate on top of the table. So we can see this actually needs us to do the goal-driven decision-making, and this decision-making is some ordered trajectory, indicating the state changes. If we try to accomplish this kind of agent decision-making, the first thing I want to do is maybe we can figure out what kind of ability we want to inject into a language model. And then we can use some theoretical framework like Markov decision process to ground this agent decision-making process. So we have two parties in the task. There are agent and there are physical world. And for the agent perspective, we firstly take the goal as an input, and then the agent will observe the environment, so they will see the state. And given the state, they will predict the action and execute the action in the physical world. So the physical world will get the reward back, and then we can get the updated state. So this is the entire Markov decision process. And the first thing we try to do is try to position the agent using the large language model or the vision language model. So they will need to handle the input, like the state estimation. So for state estimation, we're just trying to observe the environment and then translate the observation into some true world state. So the first thing we want to do is we want to build some vision language model to see the world. This actually from this image, can you see like which one is longer? Yeah, it's obviously like A is longer, but it's surprising to me when I tried it 2 years ago when GPT-4V first came out. But at that time, I think it's okay. Then I tried it today actually, and you can see like today the model still predicted wrong because this kind of feature is very similar to some visual illusion feature. And whenever the model sees the style, they will just predict that these two lines are of the same length. So I'm thinking like, if I just change the style to some different style, if we use the pencil and if we use the real image, actually the model can do them pretty well. So this makes me think the current model, when they are trying to learn the visual features, they're basically just trying to map the visual features to some semantic concepts in the caption. For example, the object concept or relation concept or action concept. But for the geometric centric features, like the shape, color, and the pose orientation, they're not that familiar by the model's annotation. So the model will not really predict well. And if we extend it to multiple objects, like we have spatial relationship and we have egocentricness, then the model will also have some problem. And then if we just extend it to a longer horizon context, we actually want the model to track the state changes and also to do mental simulation. Even if we don't see the state changes, we can imagine the state changes. And also like understanding the word transition to do manipulation and trying to build the spatial reasoning to compose the spatial memory and do navigation tasks and do episodic memory tasks. So this actually centered on the geometric information understanding. And we try to firstly see why this geometric understanding is bad. One arrogant thing I think for the language people to work on the vision language model is that we always try to linearize everything into tokens, just like language. So it works well for language, but for images, actually there are like image patches, they have geometric features. So for images and videos, if we do this way, we already see like they are not that good. And then for some like modalities that is even more structured, like charts and molecular, we actually also do the same way. So this is essentially not really fitting the model's architecture. As a result, like we always have this problem, like we feel the language reasoning is really good, but when we adapt to vision modality and other modalities, they don't really understand geometric information. So we are thinking maybe we need some abstraction layer so we can connect the language with the visual perception so they can perform much better. So here, this is what I want to talk about. Maybe we want to introduce some reasoning interface to help the model to reason. To reason about the interface, we can see there's some internal belief within the model. For example, if we have the question like place the blue chair behind the red chair, put the yellow chair behind the blue chair, put the book on top of the chair that is in front of the blue chair. So as human, we can build up this mental space just to simulate how this space will evolve. And then we can do this what if prediction over this space. For example, we can say like, if I turn right, what will behind me? As a result here, for the environment understanding, to really tackle the geometric bottleneck, we need to introduce this spatial belief. So for the spatial belief, we want the model to develop this belief to really trace back about how the different objects are located and what is the layout. So this is the first work I want to introduce about whether we could force or teach the model to build the spatial mental model and then figure out the unobserved scene. For example, if we have a space, then we could take pictures from different views. And then given the fourth view, if we have the question like what is yeah. So yeah, here, if you see like what is to the left of the black bag, actually from the fourth image itself, it's very hard to predict because the scene is unobservable. So as human, we will need to build up this mental model to connect dots between multiple images. So for example, we will firstly check the first image and we realize there's a door behind the black bag. And then we change to the second view and then we realize there's a desk. And after that, we gradually traverse different views. So we understand there's a window and there's a sofa. So this is how we compose the entire mental space. And then we just check the question like at viewpoint 4. So from viewpoint 4, we need to do mental rotation. And then this is the viewpoint 4. And then we try to see what's to the left of the black bag. So that is the window here. So this is how we try to answer the questions by connecting dots between multiple views. And this is what we human can do. But for the current machine, we try to build up a benchmark so that we can systematically evaluate whether machine has ability to do this mental simulation, build up the mental model about unobservable space. But to our surprise, the current model really has a bad performance. Like if we see the random performance is here around like 30%, then the most best model like GPT-5 is still less than 50% of the accuracy. So this is a very challenging task. Then we are thinking, we just talk about we want to teach the model to do reasoning. For this super challenge task, whether we could actually build up some reasoning interface to help model develop the internal belief of the space. So the first thing is we try to provide some scaffolding. Like if the model cannot predict what changes from viewpoint 1 to viewpoint 2, maybe we just do view interpolation. We can sample the ground truth views and inject them to the input sequences. This is very natural, but the performance is actually not good. So the model is actually just do not improve much or drop the performance. Then the second thing is maybe we just ask the model to think step by step. This is also very natural, and the performance improve a little bit, like 3%. And then we are thinking because we want to think as a like human. Then for human, when we think about the space, we always has a cognitive map to indicate the layout. So we ask the model to think through a layout like a cognitive map. And this will improve to around like 4%. So all of these are basically prompting-based approach. And we identify if we just leverage the reasoning step by step, chain of thought-based reasoning, and also leverage the cognitive map, we actually can get better result. So we use this understanding to help with the training. During training, we try multiple approaches. So we can do the reasoning based on the map and then ask the model to do chain of thought reasoning. So this is combined approach. And then this is the SFT training. We just annotate around the 10,000 cognitive map structure and ask the model to do reasoning over it. And we can see this will improve the model to around from like 30 to 40 accuracy to around like 60 based accuracy. So SFT is really helpful, as we just mentioned, but this kind of SFT really rely on a map structure. Like we want the model to think, scaffolding like a mental model. So this is how we build up this spatial belief. And here is just the cognitive map to serve as the spatial belief. After that, we are thinking what actually makes this better. If we just train the model doing like raw QA, or we train the model to do this kind of reasoning, whether the model can improve the cognitive map performance. So here we identify like before training, the model seems to be able to output the cognitive map. So the format correctness is actually close to 100. But if we check the numbers within the map, there like a similarity between the generated map and the ground truth map is super low. It's just around like 15% of accuracy. And then we try to do the training here. So if we just train the model to do the QA task like this, actually the model is able to get the cognitive map performance improved a lot, like from 20% to around 60%. This basically means if we want to do better QA, essentially what we try to improve is the ability to imagine in the space like a cognitive map. And then we already nailed down a recipe for spatial reasoning, like we want to do this kind of map, then reason approach. And then we try to see whether this is also something we can leverage in reinforcement learning. Because when we firstly do reinforcement learning, we just directly do a similar approach like SFT. And then we can see the RL approach here is less than the SFT approach. So the reinforcement learning, firstly, we don't really consider it much because we feel it's not effective as the self-supervised fine-tuning. But then after we identify this map, then reason recipe, we kind of change the RL recipe here by force the model to generate the reasoning tokens, and these reasoning tokens should be map structured. And then the RL approach actually improve a lot. So we can see here, it's basically like if we don't really demonstrate good performance in reinforcement learning, maybe there's something we can do to help the model to reason so they can actually achieve good result. So RL alone is really not working well, but we actually need the like map SFT data to help the model learn to build the map and then trying to reason over the map. So this is the first work I want to introduce that we try to reason in the space, especially try to understand how the model can do state estimation. So we have a line of work like why the spatial reasoning is hard for VLMs. And when I talk to like a student 101, I actually feel like some of you already read these papers. I'm also pretty happy about it. And for this line of work, if you have any questions or would like to talk more and collaborate more, I'm happy to talk more. Yeah, please feel free to reach out. And the second part, we just mentioned, like after we understand the space, the next thing is we try to understand the policy, like trying to identify the best action given the current status. So this policy learning to predict the action is just ask the model learn to act. So we firstly trying to build up this language agent, just use the large language model to force the model to reason, and then trying to make this RL recipe work. So if we try to make the RL work, actually there are a lot of success in the beginning of this year. So I think DeepSeek R1 basically provides this successful path that if your large language model is already good in their base performance, maybe they can leverage the verifiable reward to boost the performance by teaching the model what is correct and what is wrong. But if we try to extend this kind of RL recipe to the environment setting like the agentic task, we actually identify they are much different. So firstly, the mathematical reasoning questions, they are single turn, and our environment, they are multi-turn. And then mathematical questions, they have finite problem set, but we actually have a lot of different states. And also for the answer-wise, like we only have one answer for mathematical questions, but for the tasks, we have, even for the same goal, we have alternative paths to achieve this goal. So, and also the problem is not observed fully sometimes, like we need to handle partial observability. So essentially, we still try to leverage the Markov decision process to learn this. It's just we try to extend a single reasoning chain to this kind of state action sequences. So we have initial state action reward and state changes all over the timeline, time dimension. And then we try to use the entire multimodal multi-turn trajectory to ask the model get the reward for the entire trajectory and to update. So this part, actually a lot of people are using the single turn rollout to learn about the agentic task. So they just optimize after every action. But then we are thinking, if we really want the model to build up this planning ability, we should optimize on the entire multi-turn trajectory. So what we are doing here is like we try to ask the model to firstly interact with the environment to get the rollout. This is a multi-turn rollout. And then we use this rollout as the data to train the model using the RL algorithm. So there's two stages. One is the rollout stage, one is the update stage. In detail, if we just implement this rollout stage, it's very natural, like we use the large language model to observe the current state, and then ask the large language model to predict the action based on the entire interaction history. And this prediction, we also enhance it using the reasoning tokens. As we just mentioned, like RL will only work well if they have the reasoning tokens for LMs. So we have the reasoning tokens augmented action, and then we execute this action in the environment, and then we append all the new state and the reward back to the trajectory. So this is how we can get a multi-turn trajectory. And then we can also get a trajectory level reward. And this reward will be helpful for us to update the LMs. But this part, there are a lot of different advantage estimation strategies because we always say like RL does not work, especially like we don't spend a lot of like engineering effort. If we don't spend a lot of engineering effort on RL always does not converge. So it happens for us as well. If we try like different environment, we find the performance is pretty different. So for example, for bandit machine, Sokoban, and frozen lake, the model actually show something like the model collapse. So they will firstly improve their performance, and the performance will drop dramatically to 0. And then for web shop, this kind of environment, actually the performance will increase steadily. So we discover this, like the states in the web shop, they are mostly kind of familiar states. And later we will, yeah, please.
Oh, sorry, I didn't mean to interrupt in the middle of your sentence, but I'm wondering about, are these, I don't know the benchmarks, are these standard benchmarks? Or could you say a little bit about what the task is?
Yeah.
So we can understand.
Yeah, so the Bentley machine is more like there are two arms of the machine, and we can preset like maybe left arm represent like dragon and right arm represent phoenix, and we can give different reward to this left and the right arm, and ask the model to like select which one will get a higher reward. So this one, like the model will firstly just interact with two arms and then figure out like which one will give higher reward, and then the success rate is whether the model can select the arm with the higher reward. And for this one subsequent task, there's the agent here, and there's a target position like here, and we want the model to push the box to the target position. So the model need to make a policy about how they move to push the box, and then the box can be in the target location. Frozen lake is kind of like the model will need to move to this target, the agent will need to move to this target, and they need to avoid this lake part. And another thing, difference between these two is like for frozen lakes, their action will involve some randomness. So for example, if they say I should move to the downside, like maybe because it's kind of frozen lake, so maybe the agent will kind of get slippery, so they will slip to maybe in the middle side or some other direction. So that is kind of try to incorporate this randomness in the state changes. And for the web shop, it's just a shopping task. Yeah. And then we identify this kind of different behaviors, like the model actually will collapse in the environment that they are not very familiar with. So we call it like OOD environments. And then we try to figure out like why the RL will collapse. So the first thing we try to do is we just use this reasoning chain to explain the model's behavior. And then we check like at the first several steps, the model, when they train in different runs, we can see they will always have different reasoning chains. But if we train into a later stage, like step 150, the model will, in 3 runs, they actually get very similar reasoning chain. And it happens for the subsequent task as well. So these are the input to the model, and the model will try to, these are the output, generate the thinking tokens and the action. And we can see the thinking token actually falls into a similar reasoning pattern. So that basically means there's a echo track, like the model is echoing, the reasoning task, sorry. The model is echoing the reasoning chain that is very similar. So they kind of stuck into the repeated reasoning patterns. And what we are trying to do here is we try to introduce a monitor panel. So if you are training the RL algorithm, maybe you can check the reward variance. Like if the reward variance is very low, maybe they are already stuck into the same reasoning pattern, or you can check the gradient norm, and you can check the output entropy. So this basically means like the model is not really doing exploration, but they try to do exploitation. So they just focus one successful path, and then they basically fail because they don't really explore enough. So the next thing we try to do is we try to leverage the monitor panel and what we observed here, see whether we can make the training more stable. There's a very simple approach we try to leverage. So we already identify that when the model fails, they always have this very similar reasoning chain that has very similar reward. And then if we have very high reward, the model actually will be able to explore. So we try to encourage the model to explore more. And then we just use this reward variance as some indicator to rank all the trajectory we roll out in the first stage. And if we keep like 20% or 50% or 70% of the trajectory, actually the model's training is much more stable. So it basically means like we don't really want to leverage all the data, but the data quality is much more important than data quantity during the RL training. Like this kind of conclusion has been reviewed for the SFT setting for a long time, but for the RL setting, I think it's actually similar. Like we don't just want to densify the reward, but actually want the reward to be more accurate. And this, yeah, please.
Do you find that a KL divergence penalty does not solve that because the base model, like I'm wondering how this entropy collapse relates to a KL divergence penalty?
Yeah, so we actually have sorry. So I think here we actually try to directly use KL constraint, but it's not really helping much. But if we add it back, it actually will make the model perform better. So it's kind of some add-on
after
Yeah.
we also do the filtering.
Yeah, together. Yeah, they work together. Yeah.
Thanks.
Please.
Sure, for the multi-term rollouts, the final reward provision is outcome-based or like process report-based. I mean, each term will got different report, like the final outcomes were assigned to the same roles.
Yeah, so we just kind of add a filtering before this round of the updating. So like if you remember the architecture here, it's kind of like we first do the rollout and then we update. The ranking happens here. Yeah, so yeah, it's true. Like you mentioned, it will use the last round of the reward.
So we're trying to do is have like sparse work to more diverse. You find out like the class disappears or like the diversification of the report then.
Yeah, so we found that if the reward is more diverse, then it basically means the model is trying to explore. So they will not have this kind of collapse kind of symptom. And then we actually observe the model training like this. So at least they will not drop dramatically. But as you mentioned, there are still a lot of problems. So we will talk about how we try to solve it. One problem is that the success rate is still super low, like only 20%. And that basically indicates the model is still not exploring enough. Yeah. Yeah, so here, I think we just mentioned that we want to encourage the model to explore, especially in the OOD environments that is unfamiliar. So here we firstly try to quantify the OOD environment. So we can see for the state, the model is not very familiar with the state representation. Like we can just simply use perplexity and we can see Sokoban and Frozen Lakes, their state is much more, their perplexity is much more higher than web shop. And then we can see whether we could track the passet 1, passet k, this kind of metrics to indicate the exploration and exploitation. So one thing here is like the model, if we check the web shop, this kind of training curve, we can see a web shop training curve is increasing in passet k and also passet 1. But for the current model in like Sokoban task, we can see their passet 1 is basically not improving much, and the passet k sometimes will drop or also like not increasing. So we kind of feel there's a divergence between passet 1 and passet k, and the passet k metric is actually more indicative about whether it's explore the environment or not. So we will also try to optimize the passet k later. And then the key question is we try to encourage the exploration, but how we can do that? And our current solution is we try to make sure this reasoning approach, reasoning tokens are trying to build up this internal belief of the environment because there's an environment that is new and the model's major learning curve should be grounded to the understanding of the environment. So this is essentially very similar to word modeling that we try to understand the environment. Then we try to introduce the word modeling reward for the VLM agents. So for this work, the important thing is when we're trying to understand the environment, sometimes we're not only trying to just handle the text state like the Sokoban task. On the left side, we can convert them into text, but we also want to handle this visual input like images. So this actually makes us to think the previous MDP process maybe should be changed to POM-DP, partially observable MDP. So essentially, what we are doing here is we have the MDP process and we want the model to learn the state transition. But then we have to change it to POM-DP because we have the observation and we ask the model to observe first and then execute the action to get to the next state. So here we want the model to have better reasoning on the to build up their internal belief. So we firstly ask the model to do the state estimation. So given the observation, they should actually think about what they observe from this environment. And for the visual input is essentially a grounding task. And we have different kind of grounding abilities about the robotics. We try to ask the model to figure out whether they could locate objects into a kind of map-based structure. And then we ask the model to reason about, given the current state, can you predict what is the next action we want to execute? So the model will say, like, first I need to pick up the red cube and place it on top of the green cube. And then the model will try to simulate what will happen next. So this is kind of pure mental simulation. And the model will simulate what is the new position of these different cubes. And then they will predict the action and execute this action in the environment so we can get the next state and the next observation and build up the new internal belief. And then we can calculate the reward to optimize the RL algorithm. So here the key question is how we can represent and learn this internal belief. For the different tasks, we actually identify they have very different preference about internal belief representation. So for example, for this circle task, we can actually translate them into the symbolic based representation easily. And for the robot manipulation task, we actually translate them to this JSON based structure. And then we also recognize like for some tasks, natural language will be better. Like we actually use like frozen lake, we actually use natural language to represent the internal belief. We just talk about like we try to build up the internal belief to optimize from the MDP process to POM-DP process. But what we really optimize here is essentially trying to capture the state changes like a world model. And then for the POM-DP, we have something new like the observation here. And the observation will push us to not only just learn the state transition, but also trying to learn the state estimation. So essentially, this is a world modeling process that we want the model to learn the state estimation first, and then learn the transition model about next state. So we should try to like not only leverage this world model to help with the RL thinking, but also maybe we could leverage this world modeling to help with the RL reward shaping as well. So here, for the reward shaping part, we firstly ask the model to predict the current observation using a format like this observation tag. So this is also inspired by DeepSeek R1, like they can introduce the format reward based on this. So we also have the format reward to push the model have this observation tag. And then we can have the predicted status and the ground truth status. There are two language sequences, so we can use the large language model as a judge to get the reward. And then we can ask the model to do the next state prediction. So this part, we ask the model to get the prediction tag generated. And then we can calculate the reward between the predicted next state and the ground truth next state. And then we can see this world modeling performance is actually pretty good. So here, the blue line means like we just use the format reward. And the orange line means like we also calculate the reward between the ground truth next state and current state. So here, the orange line has the reward shaping. And we can see like the orange line actually increased the blue line a little bit. But if we compare to all the base model, they are all the same size. And we can see like for Q1 and other like VLM R1 based approach or other PPO, GRPO approach, I think this reasoning based on the world modeling really help a lot. So essentially just push the model to reason this way will help the model to explore. And then we can also compare with the closed source model, like the GPT models and Gemini models and cloud models. So we can see like the model's performance is still not that bad compared to the closed source model. And we also observe like for the model reasoning part, like the robot manipulation, they highly rely on this JSON-based representation. And for the SVG-based tasks, this kind of exploration or thinking about next state will also be helpful and actually help model to do the SVG QA task. So this actually trying to show that we not only want the model to act, but they try to explore more about the state, and they should see the state and act together. So this is what we try to build about the RAGEN and VIGEN RL training framework. And if you try to add your own environment to it and have any questions, you can also feel free to let us know. So we actively monitor the GitHub issues. So yeah, and then the next thing is we just talk about world model, and we talk about how the world modeling can be helpful for the online RL training. And another thing is we also discovered earlier the SFT stage is very important, and we talk about the current OOD environment do not really have a very good understanding about the states, so the lack of SFT stage. So here we are thinking like maybe we should just mimic what children is doing about learning the environment. They don't just learn the environment by completing some task and get the reward. What they do is they just self-play with the environment. They don't really have a goal. They don't need to like have some ground truth trajectory to optimize. They only need to understand like if I interact with the environment this way, what will be changes. So this is kind of like freestyle interaction. So what we try to do is we just have some action here, and we ask the model to learn about like what is the current observation and what is the prediction. So this is kind of like we make the SFT more about interacting with the world just with single action. And then we construct a lot of SFT data based on this, but actually the model is not really working well. And then we change it to something like maybe we should make this exploration, this self-play to be grounded to the model's original internal distribution. So we should do something like we can firstly ask the model to generate a lot of trajectory, and we don't really care whether the trajectory is correct or not. So it actually has a lot of wrong trajectories. And then for each trajectory, for each action, we will just replace the wrong observation and prediction with the ground truth observation and prediction. It's very similar to teacher forcing, but essentially we just ask the model to based on like what kind of action they really care about, and then directly learn about these specific actions. This actually makes the model perform super good. So compared to the previous model, so like if we just directly use the RO training, we mentioned they always have something like their path 1 is stable and their path k sometimes will drop. And here, if we try to ask the model to have this self-play, this SPA means self-play agent, so we can see the model's path k actually can improve a lot as well. So this means like the model is really trying to explore the environment because they have this kind of self-play data to build a foundation for them, and they have the ability to bootstrap themselves to further explore the environment. Yeah, so I think here we just talk about this different ability state estimation, MDP policy, and how we build up the reward model using the word modeling. And I think here this kind of entire process is like an agent interface that's trying to connect the foundation model with the environment. So we built up this embodied agent interface to make the model able to connect or interact with different embodied environment like virtual home behavior. And then based on this interface, we have this 4 different components included. The first one is goal interpretation, and then the next one is like action sequencing, sub-goal decomposition, and then we model this word modeling part like a transition modeling. And then these 4 components will be composed all together like the embodied agent interface, so they can connect with the any kind of environment using this large language model. So we just talk about how we can make the large language model to interact with the environment and how they can do the goal-driven decision making. And essentially for the environment part, we have a lot of ability centric on the geometric information that is not good. So we want the model to build up the internal belief of the word to better do the reasoning. And for the decision-making part, we ground it to the MDP policy, and we try to learn better state estimation, MDP policy, and the reward model. And then there's another part like goal interpretation. We didn't cover much in this work, but in our agent interface, we actually cover this one. And then this framework has been grounded to our tutorial about how we can categorize all the robotic foundation models recent years into this different category. So you can see like different methods, actually they're just different about how they do the state estimation or how they design the reward model or how they design the transition model part. So if you are interested in learning about how to use like MDP lens to understand the embodied agent, please feel free to check this tutorial. And we also have a foundation model challenge for the embodied decision making, and this is at Neurops, and we will do in November. So if you are interested in this, also please feel free to participate. And we also have like 1,000 for like first prize. And yeah, we recently also released with some data analysis tool, and if you want to leverage some data analysis tool, you can also feel free to use it. So I just built up my lab for around like 1 year, and I actually like named my lab very similar to my own name. I can interpret it as like machine learning and language. So yeah, I'm happy to take any questions.